I'm Professor Frank Supp. Thank you all for joining us today for the defense of Mark Price for his dissertation, his PhD dissertation. We're joined by his committee members, Professor Brian Umberger at the University of Michigan. And we're also joined by his other committee member, Professor Ian Gross here from the Department of Mechanical Industrial Engineering here at UMass. Today, so real pleasure here to present or to have the honor of introducing Mark Price's dissertation defense. Mark joined us from Georgia Tech, where he finished his undergraduate degree, and then he got his graduate degree here, a master's degree, and he's continued on the fund today to finish his PhD. So we're really excited to hear more about the work that he's been able to do, and again, more amazingly, the work that he's been able to do over the last 6-7 months during the pandemic, actually getting a pause from lab work, getting things done in his apartment, and then actually getting some limited access back into the laboratory to gain the results that you'll see presented here today. So with that, thank you, Mark, for presenting, and please go ahead and begin.
All right, well, thanks everybody for coming, and thanks to my committee for coming especially. Yeah, so let's get started. Okay, so there are a lot of people living in this country with limb loss, and that number is only increasing. We have about 2 million estimated right now, expected to go up to about 3.6 million in the next 30 years. That's not just population growth. The main reason this number is going up is because more people are getting vascular disease like diabetes, which, among others, is the leading cause for amputation currently, over half. And well over half of those are going to have lower limb amputations. So that's why I'm focusing on lower limb amputation in particular. So once you lose part of your leg, what do? Well, you adapt and you find ways to compensate. But these compensations can have some negative effects of their own, and some effects may persist despite adaptations or even because of them. So needless to say, you're working with different tools than you had before. So you have to relearn how to do some things, and the muscles you have left have to compensate. What this often means is even after a while, you still usually will have a higher energy cost to perform most tasks. You're going to be less stable, and often you'll have discomfort in your residual limb where it interfaces with the socket that attaches the prosthesis to your body. And what this combination often leads to are some long-term problems later on, where probably the leading one that gets the most attention right now is you become a pretty high risk person for developing osteoarthritis, pictured on the right here, which is usually once the process begins, it's not reversible and often terminates in a total knee replacement or maybe multiple total knee replacements over the course of your life. But aside from that, other effects have been noted. You'll have reduced bone density a lot of the time, chronic back pain. That residual limb discomfort can turn into pressure ulcers, and often you'll have muscle atrophy and in general, just an overall decline in your activity level because things are simply harder to do. So knowing all that stuff, how do we improve these outcomes? Well, maybe the most clear and obvious proposal would be you're missing part of your body. So probably you should replace that part of your body with something that does the same thing. Fortunately, we have a lot of people who have been basically trying to do that, and they've come pretty close in some important ways. So this, for example, is now known as the Autobach M-Power. It's a commercially available powered ankle prosthesis, formerly known as the Biome project out of MIT. And without getting into too much low-level detail here, what I'm showing you in these plots is that in the blue diamonds is what the prosthesis does, and the gray and green within that range is what you would expect a person with their biological ankle to do as they walk. And so they've already gotten very close in terms of the angle relationship to their walking speed and the amount of work that their prosthesis does relative to the amount of work that you would expect a biological ankle to do. And in fact, even more work than you would expect it to do at these lower speeds. So we're doing pretty good there. Here's another example. This is called an ankle foot emulator because it's designed mainly for laboratory testing. It has this big off-board motor that is tethered to it, and that's been developed first at Carnegie Mellon, and the project is sort of ongoing at Stanford right now. And these are slightly different plots where what we're looking at here is the torque relationship to ankle angle, which is a common way to model the overall ankle behavior. And they are targeting this curve. And what you can see on the right is that they've been mostly successful in reproducing it, the blue curve being what their prosthesis actually does, and that dotted line being what it's trying to do, which is matching up quite well with what the biological ankle does. And one more example out of Vanderbilt, my advisor's alma mater. We have a powered ankle that here we're looking at just the kinematics, so the ankle angle and the ankle torque over the gait cycle rather than in relation to each other. And again, we're saying it's not exactly between the lines, but it's very close most of the time. So I guess the question is, if we can do that and we have a bunch of people that can do this, is it working? And the answer is basically kind of, but it depends on who's wearing it. So for example, if you look at the emulator projects, this is 6 subjects that they tested. And on the x-axis here, as it increases, that is the work provided, or basically the energy provided by the prosthetic ankle. And then on the y-axis, you have the amount of energy it takes to walk. And so what you would hope to see is a downward to the right slope. And what you probably have noticed is that nobody has that. Actually, this one, subject 3, kind of has the opposite of that. And so we're left kind of wondering why, if that is the case, maybe some of our assumptions are faulty. Another example, this is that commercialized ankle, the Ottobock M-Power. These are 2 different metrics I'm looking at here, but the important thing to note is that this is an osteoarthritis risk factor that's been associated with future development of the condition, which is adduction moment on the knee. And if we compare the passive prosthesis, which is the black line, and then the white line, which is the biome or the M-Power, whatever you're calling it, they found basically no real difference in this metric, at least for this subject population, which notably, they were already in pretty good physical shape. And so they were able to walk fairly well without the assistance of the powered ankle. And they found that it didn't really help, at least in this case. Whereas on the right here, we're looking at from the publication that these people, the developers of this ankle themselves put out, it's metabolic cost of walking in relation to the walking speed. And they see that the blue and the green, which is able-bodied and prosthesis, are pretty close to each other for the beginning, but they begin to diverge as walking speed increases. Still much better than not having the powered prosthesis, but certainly not the same. It's not replacing it exactly. And so the question is, why is that? And I guess the answer I'm coming to is that when you replicate the biological joint the joint behavior in isolation, so the joint is doing everything it's supposed to do in the biological joint, but it's not enough by itself because the entire system above the joint has also changed a lot. Illustrated kind of on the left here, just by the fact that once you've removed these muscles and part of this limb and all of these segments below, that really changes the way that your body interacts with the ground, because now you have this extra interface where before you had these load-bearing tissues, load-bearing bone in compression. Now it's all being transferred to your body through the soft tissue interface that was not originally doing that. In addition, the actual socket pressures, depending on where you are in the limb, like certain parts of that limb do not handle pressure well, as marked by this orange spot. And that also depends on the post-amputation anatomy, which is different from person to person. People have different socket designs, socket suspension types. Some people have end-bearing residual limbs where they've grafted the heel onto the bottom of the limb so that they can basically stand on it directly instead of like this where you're more suspended from the sides, and so on. There's a lot of variation just in this connection alone that is completely ignored by any attempt to replicate the ankle joint behavior by itself. And then finally, in addition to that, just losing the nerves, the feedback and the control, we can't really interface that directly into the nervous system right now. And so it changes the way you're going to behave pretty much no matter what. Your confidence in walking, where your foot is, how you're going to respond in the moment to unexpected conditions, etc. That's all going to change. So I guess the bigger question is, again, how do we improve user outcomes? We can kind of revise our proposition here, where rather than replicating the biological joint, maybe what we should be doing is testing these design factors experimentally to discover what actual effects they have and what actually works in improving selected user outcomes. I'm gonna move my Zoom little window here because it's blocking my view. There we go. Okay, so here's an example of some people who are also doing that. Just a couple of these real quick, but this is a configurable passive device where they've made it so that you can adjust the stiffness of this passive joint. So the torque angle relationship is tunable to the user. And I know that they've done studies where they allowed the user to control this themselves and find their own preferred stiffness and figure out what that should be and why. Another couple examples, moving on from that emulator project, they've started basically just adding toes. So they went to 2 and now they have 3. For the second toe, what that gives you the ability to do is kind of, you now have control over out of plane moment as well. And then in the third one, this is kind of getting even further away, where now you have a backwards facing toe and you can control the location of the center of pressure and see how people respond to that. So going back to if this actually works or not, it certainly improves our knowledge base regarding the effects of design variables on user outcomes. And there have been some work shown that like you can get better outcomes by doing this, but it's more of a learning process than it is like a design change. But it's kind of limited in some ways in that you have to basically decide which variable you're going to look at based on usually the context of the biological joint and your general understanding of the physics of the problem. And often the design form pretty much imitates known designs already, or more typically the biological ankle itself. Again, despite the fact that we're dealing with problems that really change the system above the ankle as well. So I'm sort of positing here that the unanticipated non-anatomical prosthesis behaviors, if we allowed them, might improve user outcomes more than the existing design forms would allow for. So how could we do that? This is my approach that I invite you to go through this thought experiment where basically pretend that you don't know what an ankle looks like or a foot. You don't know what it does. All you know is you need something between your leg and the floor. And your body doesn't care what that is. Your body experiences that device as the interaction forces based on its relationship with the environment. So one way we might be able to take advantage of this is if we can solve for those forces such that they maximize some measure for these user outcomes that we're targeting, then hypothetically, we would know how the prosthesis should function in order to improve those outcomes without limiting ourselves to a design form from the beginning. So one way this might take place, if say you want to reduce the energy cost of walking, if you can solve this math problem such that energy cost of walking depends on what these forces are, and you can solve that problem so that you can minimize that objective such that the system dynamics of walking are correct and enforced, then your optimized output could be translated into a real world design. So that kind of brings me to my proposition of how we might be able to do this, which is simulate a generic prosthesis to discover unanticipated design factors that improve those user outcomes. So yeah, does it work? We don't know yet. That's why we're all here. So that brings me to my objective. I am creating a design method which will take simulated generic prosthesis behaviors and translate them into an actual design, and also create the tool set so that we can use this design process and refine it through experimental testing. So I kind of see this whole approach as sort of a flow chart with a feedback loop where we're simulating, as I described before, then we're designing to turn those simulation outputs into something that you can really put on someone and have them walk with. We're controlling that device so that it actually recreates the key aspects of the simulated behavior. And then we're testing with subjects to validate the simulated effects. And that's a pretty important step because if we don't do that, we have no real reason to believe that whatever we come up with from the simulation is actually going to be helpful. It's probably not going to be exactly right, but we at least can find out if we're looking in the right direction and refine the simulation based on the information we gained from testing. So I'm going to focus on this work on these 3 steps. This is pretty much, these 3 steps are the sort of infrastructure that allow this whole loop to occur in the first place. Once you have that, then you can do your testing and refinement and then repeat. But this is the stuff that really needs to get done in order to enable this whole flowchart to exist. And I'm going to start by talking about the simulations in more detail, which I covered in a pretty cursory fashion just a minute ago. Okay, so how do we do that? How do we simulate these people walking in a way that we think they will actually walk? Well, I'm using OpenSim. It's a software, open source neuromusculoskeletal modeling and simulation software. And you can see on the left here, this is basically a top level flow chart of how it works, but basically you have muscles, they exert forces on the body, which you can define how the joints behave, you calculate the physics, you get out the motion, and then you go from there. Pretty much the defining method that uses these, this model, I should say, is that if you want to investigate what someone will do based on this model-based approach, you kind of have to have some inclination of how they are controlling their muscles. And so, first of all, we know that we can calculate the system dynamics through the model based on muscle inputs. We also know, and I put some citations here, but I see that that didn't make it into this version of the presentation, so I apologize for that. But we do know that human gait tends toward patterns that minimize energy consumption. So it follows that gait can be reasonably approximated by optimizing muscle inputs to minimize the effort spent by the person. And these are a few examples of how that has been done through the past several years. Wow, the lights did turn on. That's unfortunate. And what we're looking at here are just joint angles. predicted by this sort of approach where you optimize muscle inputs to minimize effort in some calculation or another. And what we find is without enforcing gait-like patterns, we get them anyway. They're not perfect, but they're pretty close. So if we extrapolate from there, if we look at someone walking with a prosthesis, which we also can control, so we have 15, in this model in particular, we have 15 muscles, 12 body segments, removed the 3 muscles that cross the ankle joint on the prosthesis side, put in these ideal actuators and also treat them as controls to the model, which gives us the ability to lock the translational forces, so the linear Fx and Fy here. If we lock those, we can also simulate your standard revolute joint or any combination of these as well. We're introducing socket motion and forces to account for the fact that we are considering this problem as part of the prosthesis design problem. And then we have a contact model so that our external loads from the environment are transferred through the body and affect how we move. So if I look at the primary 2 optimization objectives that I've selected for this study, I'm looking at user effort and socket discomfort primarily as my user outcomes. These equations here are describing how I'm actually calculating those, how I'm defining user effort, for example, is as muscle activations, which are basically your muscles, you can assign them a value from 0 to 1 to give an indication of how much force they are producing at any given time in a very rough manner of speaking. OpenSim has muscle models in it that sort of handle all these more complex muscle dynamics, but the muscle activation is a good indicator of how active your muscles are. And if you sum those for all of the muscles over the whole gait cycle and then average them, it gives you a pretty good indicator of how much effort the person is spending. And then for socket load, what I'm looking at is for both of those degrees of freedom. So we have that pistoning up and down, and then we have that flexing forward and back. And we're taking those loads and we're approximating a maximum load by raising them to the power of 10, which is then normalized so that you don't get gigantic numbers. But what that effectively does is it penalizes outliers and effectively approximates just taking a maximum. Because what we really care about here in this case is not the overall amount of load, which you can't really reduce beyond a certain point. You have to support the body somehow. But what you can do is smooth out that curve so you don't get these load spikes that can actually cause tissue damage over time. And so the question we need to ask is, first of all, how important are these objectives relative to each other? Is there a trade-off? And how much can we actually constrain that motion of the prosthesis before we start losing performance, before we start having to spend more effort and endure higher loads? So I formulate this objective function. There are 2 additional terms here, which I basically am using to regulate the output of the simulation. So this epsilon here is like 3 orders of magnitude below the effort function, which I'm treating as the default sort of normalized value. So what they're basically doing is they're not substantially changing how the prosthesis should work, but it does provide some minor penalty for unnecessarily making the prosthesis output like free energy, like 10,000 watts or something, which we can't really do. And then also prevents it from doing things that you wouldn't really expect a person to do. Like it forces it to walk a little bit more normally. I realize that kind of contradicts some of what I've said earlier, in that we're trying to avoid assuming biological mimicry. But my sort of take on this is if we learn enough about what this function should actually be, that it really replicates how a person does behave when they walk, then that term will no longer be necessary because we'll have replaced it with terms that have actual physical meaning. Anyway, so I'm varying the amount of loading relative to the amount of effort, And then I'm running it over a variety of different simulation conditions where the walking speed goes from slow to fast, the socket stiffness goes from less to more stiff than some nominal value, and then changing the number of degrees of freedom in the prosthesis as well to see, if we go from revolute to this full unrestricted planar motion, how much of a penalty is there in scaling that back? So if we look at how important is each objective, what I find here when I'm comparing just the revolute model and the 3 degree of freedom generalized model, it's more clear in the revolute model that this alpha of 10 to the minus 1 or 0.1 is the most balanced solution between them. And it's kind of apparent in this model as well. It's not as obvious, but where you can really notice it is that these standard deviations in the x-axis are getting really wide, and that's for muscle effort. So it's saying, as I increase this term, some of them optimize very well and have pretty low muscle effort in line with the rest, and some of them have ridiculously high muscle effort expended just to satisfy this condition. So it is less consistent, so I ended up sticking with this alpha of 10 to the negative 1. And what I found also is that if we do constrain that generalized model to a revolute model, it's worse in both respects. The generalized model reduced the socket load peaks by 15%, and the amount of effort spent by that metric by about 30% on average. And if I compare all 3 models, this is what they look like when they're walking. So on the left, you have your standard revolute joint. It looks a lot more normal other than the fact that it's floating in space. The other one, the 2 degree of freedom, that's with rotation and 1 linear degree of freedom that I optimized which angle of that degree of freedom would improve these the most. And what's kind of interesting is that once I did that, I actually got better performance than the fully unrestricted one, which could possibly be explained by the fact that I'm using a gradient descent method for optimizing these functions. It's the interior point optimization algorithm. And what that means is that it's pretty sensitive to the initial guess, especially for something with this many variables. So what this tells me is that I probably actually didn't have the best minimum for the overall 3 degree of freedom. It might be trapped in a local minimum because I can't imagine that it would underperform a more restricted solution, but I suppose anything's possible. However, what this proved to me at least is that you can do 2 degrees of freedom if you just figure out what angle that 2nd degree of freedom is supposed to be at, and be very competitive at the very least with a fully unrestricted planar motion solution, which is also 2 degrees of freedom is a lot easier to design, which brings me to my next section in actually designing something that walks like that. So as far as the objectives of the design, I'm trying to make something that can replicate these prosthesis dynamics. I've been talking about this over and over again. What that kind of means is I also need to make it flexible in that it's not just able to reproduce this set of results. It should be able to reproduce other sets of results from other simulations where I change the conditions and so on, so I can continue to adapt the method as I've talked about. It needs to be wearable, and by which I mean it can't be super heavy, or else it's going to probably mitigate all of the factors that it's supposed to be helping with. Like if it's 10 pounds on the end of your leg that you have to swing around, your amount of effort you have to spend to walk is probably going to be way higher, regardless of how much it's helping you technically. And then I want it to be untethered, because while you can do some useful things on treadmills tethered to like an off-board station, it does limit what you can do relative to overground testing. So for example, you can't do things like stair climbing as easily if you wanted to investigate that. So this was a priority. So what this led me to come up with in terms of a very general design concept was I needed these 2 degrees of freedom to remain independent rather than trying to couple them and achieve like with a single actuated mechanism, that same behavior. I know that I cannot get something with those 2 degrees of freedom with both actuators with that much translation range, small and light enough that it will be practical to wear if all of the motors and electronics are located on the prosthesis itself. So I'm designing a prosthesis that you wear and a wearable offboard control system. So it's kind of a compromise between the biome design where everything is self-contained inside the ankle and the emulator design where you have really big motors way off on the side that can basically well exceed anything that the biology can do or most prostheses can do, but you're tied to a table. So this is a big confusing slide, but what I'm trying to show here is that these are the actual output curves of that solution that I showed the animation of earlier. And what this allows us to do is come up with design specifications that can meet this level of performance at least. So you can pretty much take the minimum and maximum of all of these graphs, except for maybe this last one. And that gives you a lot of information in terms of what the design needs to be able to do. So it gives you range of motion, that's the first plot here. And what we're finding is that in translation, the linear translation degree of freedom pretty much always just goes from minimum to maximum. You're seeing it flatten out at 0.05 because that was the simulation constraint. I didn't allow it to move more than that because I didn't think it would be practical to design something that big. And it used all of it. So that kind of gives us some indication of what this is going to be used for. Whereas on the other hand, in plantar flexion, which is the foot turning downward, that is pretty much just it's starting at a neutral position and then pushing off down toward toe off, which is, while the shape of the curve is a little different from biology, it's basically the same idea in that it pushes off downward at the end of stance. And then this also tells us how much force or torque the prosthesis needs to be able to provide over the stance phase. And it doesn't just tell us the maximum amount, but it also tells us what the continuous region of the motor should be. Because you can see on at least this top plot, it stays at about -100 at least for almost the entire time, which means that the motor cannot be maxing out at 200. It has to be a bit more than that so that its continuous operation region can handle operating at 100 for a long period of time. And the same with this, I'm marking it off at 50 Newton meters just because that's where it kind of has this crossing at the very beginning and the very end. And it goes up to about 120 Newton meters as the maximum. So that brings me to the concept of the actual design itself. I already talked about separating the degrees of freedom to make them independent. So as a very basic sort of block diagram schematic, how that might be accomplished. I've already talked about making an off-board actuation system. So that means the hardware on the ankle is all cable actuated. So there are no motors on the ankle itself. All of the power is coming through these cables from the off-board system and transferring that load to the prosthesis. So what I've determined here is for translation, since it's going from one end to the other pretty much back and forth as far as it can, it needs to have bidirectional control, which means it needs 2 cables because the cables will only exert force and tension. Whereas with the flexion axis, it's pretty much all in one direction, at least all the power is. It's all in plantar flexion, which means I can get away with one that produces power pushing the foot down, pulling the heel up, and just having a spring return it back to a neutral position. As far as the actuation goes, this is sort of schematics for what's happening in the off-board system. I ended up deciding to do a linear actuator for the flexion axis since it requires a much more aggressive gear reduction. And the idea being, this is, at least with a ball screw, is a much more efficient mechanism mechanically. So you get more of the energy out that you put into the motor than you would if you just did a traditional motor and gear head, which is what I'm doing on the winch system, which is more about speed and less about force. And this is just sort of a schematic of what that looks like from the front, where you have a translating load and you're just turning this winch drum one direction or another, and it pulls in either direction. So one of these cables is always in tension. So if I go to what the actual design looks like, going from those sketches, basically, this is a CAD model of the final design that you can sort of see behind me here. I have the cable actuation coming through here. I have a 3D printed foot that sort of acts like a traditional elastic energy storage and return prosthetic foot, where it's meant to be somewhat spring-like in its behavior, which also gives me a sort of leaf spring lever in the back, which I'll talk about characterizing that more later, but essentially it makes it a built-in series elastic actuator. I'm making a lot of liberal use of 3D printing parts so I can combine them. For example, these Bowden cable conduit mounts. These are also structural pieces of the frame. And then as for a cross section here, you can see how this thing is sliding forward and back. It's on a set of rails, and these pulleys just come through right in the middle and hook on through the same axis in between these guide rails. And that's what it looks like, all constructed. I've pretty much described what all these are. There's a enclosure on the back with a tether for the actual onboard sensing, which I'll discuss in a minute. But this is how it corresponds to this simulated behavior, which I've tried to illustrate, the ranges of motion displayed in the simulation. So you can see it's moving up and down on this slider thing here, and the foot is going up and down. And I'm replicating the range of motion possible in the prosthesis in the CAD model to show that it matches up pretty much exactly with what that OpenSim model is doing. As far as the actuator pack, I know this slide is kind of a mess just because you just see a huge bundle of wires and electronics inside of a backpack, but this is a nice clean look at it. And if I turn my camera slightly, you can see it over here. It doesn't look so bad from the outside, but it's got a nice cooling fan. It's got a signal tether coming out, and the Bowden cables are attached rigidly down here. So they come out the bottom, and the actuation mechanisms are mounted so that all of the cables are being pulled up through the bottom. You can also see these two green boards here. These are Maxon motor drivers, so I did not design my own. I used the ones that they have, which take up kind of a lot of space. Another reason I wanted to put this on your back rather than on the shank. And then these two purple boards are ones that I designed and built. One of them is an emergency stop relay, where you can see this handheld button. If that button comes out while the motors are on, the motor's cut off immediately. So in case something goes wrong, you have the power to deactivate it without worrying about the control logic or the code or whatever getting hung up on something. And then finally down here, we have a wireless control unit that is a board that I designed. It's an embedded system that interfaces with a Raspberry Pi. And what that basically is doing is it communicates through Wi-Fi to a host PC that's running Simulink. So if you program all of your control and all of your signal processing and stuff through MATLAB or Simulink, you can control this whole thing wirelessly through Wi-Fi, and it will provide all of the low-level motor signals and stuff to these drivers. So that's how it actually looks when it's fully assembled, and this is the nice clean CAD rendering. As far as sensing, so there's a few onboard sensors on the prototype itself. I have encoders to measure the flexion and translation positions. One of them is a linear slider, and then one of them is just your typical rotary encoder. And then there's a board on the back here that I also designed to mount an accelerometer. So when you get an acceleration spike, it's a good indicator that your heel just hit the ground, which is what allows it to adjust to your step duration. And then all these other electronics which handle the signal processing and send them up to the main board on the prosthetic or on the backpack. And then a combination of these sensors is what forms the actual ability to sense the force and torque. Now, I mentioned earlier that there's a series elastic element designed into the foot, which provides some elastic repeatability for how the plantar flexion axis behaves. So you'll see that on the right plot here, I'm able to sense torque with about a 7 Newton-meter margin of error, at least RMS. There's still some hysteresis effect notable as it comes unloading. It wants to come over the top, but it's much more exaggerated in the translation axis where it's pretty linear. And then as soon as I start unloading it, it just wants to stick there. And the reason for that is the cables are literally sticking inside their conduits because they need to stretch and move in order for this measurement to work properly. And so having that extra compliance built in that's more regular helps offset that. But for this, I didn't do it because as we saw from previous slides, the translation performance is pretty much just positioning it from one end to the other. So I felt that load sensing, rather than designing in a whole series elastic actuator component into what's pretty small geometry, I instead just dealt with a more rough qualitative estimate of what the force is so that I could position it and use the force feedback as more of a limiting guide so that it doesn't push too hard against someone if they're trying to fight it. Going into the actuator limits, this is an example of how I tested that. This is the motor being saturated at 15 amps, 40 volts. You can see these springs under the desk that are being stretched until the motor gets installed. And you can watch how much that foot flexes at the back when the view comes over the top. It's pretty substantial. And that's working as designed, and that's why that load measurement is more reliable. What I found was that it could pull up to 171 Newton meters of torque. It moves at about 1 radian per second and about 113 watts of power output at its maximum, which is lower than I designed for. And I can discuss that later in terms of like the design limitations. But basically, I think that my ideal linear actuator design was a bit of a wishful thinking in terms of what can be achieved with a ball screw linear actuator versus putting one in this sort of backpack environment where you don't have a super rigid support structure around it. Because you can see from the other axis, translation axis, while it gets up to approximately 500 Newtons, the speed that it got to is more in line with what I expected, and the power output is over 200 watts, which is good. That's about right. So that kind of brings me to, when I look at final specifications, I didn't talk specifically about mass and height earlier, but these are based on similar ankles. So I fell in under what I was aiming for. And I met pretty much all of these, except it's too slow, basically. It's slower than I thought it would be. So we'll see how much of a problem that is when I go into the control section. So here I've updated the simulation with the actual prosthesis. So it has all the masses of the real assembly. It has the actual elasticity of the foot modeled in, and it has the cable actuation modeled in as well. And so the objective here is, if we have the simulated behavior, now that we have hardware that can theoretically accomplish that behavior, I need to actually make it do it. And so the way I've decided to do that is to use an impedance controller. This is useful for wearable robots especially, because rather than telling a motor where to go or how hard to push, it sort of does both at the same time, where instead you're creating sort of an interaction model where the motor pretends that it's a spring, and you can set how stiff that spring is and where its default unstretched position should be. And that position can be moving. So it gives you this sort of compliant behavior. You can design in compliance that's not physically there, and you can tune that compliance to achieve the behavior that you want it to. In this case, our targeted simulation behavior. So an example of how that works, if we separate the stance phase into phases where we can sort of see individual joint motion patterns, and we minimize the controller output force against the simulated force by changing these stiffness and set point variables, then we get something like this, where we can, based on this displacement here, the difference between this set point, which I'm optimizing, and the actual position, and the stiffness that you can't see modeled here, that gives us an output force in the blue line that I'm trying to match as closely as possible with this black line, the simulated force, plus or minus the standard deviation from all the different parameters I was simulating. So these are two speeds, the slowest and the fastest speed that I simulated. And you can sort of see there's some different modalities here, where one of them has what looks like 4 phases, where it goes level here, then it goes sharply up, and then it goes more level, but still going up, and then it sharply goes back down to the actual value as torque drops to 0. Whereas for the faster speed, it just has time to do one of those increasing set point patterns, and then does the same thing at the end. And so I came up with optimized controller parameters for 4 different walking speeds, 0.9, 1.1, 1.3, and 1.5 meters per second. And I put them all in my controller, but I'll explain exactly how that works in a minute. What I just showed you is this part of the overall control architecture. It's relatively small, but it's perhaps the most important as far as the actual simulation imitation contribution of the work, where you have the actual position coming in, comparing against the desired set point, which is generated by a walking state machine, and the tunable stiffness. And that goes into a load control loop, which I'm using load to just refer to both force and torque since we're doing both. So that whatever force we're asking it to give us, it's capable of giving it to us. But before I go into that, I'm going to talk about the very top level first, the walking state machine. The way that works basically is once this Y triple dot refers to the jerk, or the time derivative of the acceleration as measured by the accelerometer on the back of the prototype. And it's specifically the vertical one, because I found that because it snaps forward and back, if you can include the horizontal component of that, you're going to get false heel strikes every time it moves. So if you use only the vertical jerk, and it's above some threshold that you say, above this value means that your foot just hit the ground, then it begins the stance phase, where it proceeds through all of your subphases based on the percentage estimated of stance that you've proceeded through. And it knows this percentage based on the amount of time it took last time to get through stance. So it takes one step to kind of calibrate this before it really activates and begins adjusting. And once you've got through the last phase, once torque falls below a certain threshold, it means that it's no longer pushing you off the ground and your foot's about to leave the ground, which means it can go into swing phase, which is just 2 phases. The first one gets the foot out of the way so you can go swing forward. And then the second one resets it to the start position for the stance phase so that it's ready to go once you hit the ground. And so that once you actually do hit the ground, if you stop walking, it should hopefully hold that position. So we've talked about the top level and the impedance controller, and I'm going to talk briefly about how it controls force. So if I zoom in on that, it's just a PD controller where you have our estimated force, which comes from that difference between the motor output and the prosthesis output, multiplied by the stiffness of the transmission. That gives us our estimate of the load that we use as our negative feedback into a PD controller. However, instead of a typical derivative term of the force, based on some other publications from people doing similar like cable actuated force control, which is exactly what this is. So I had some help in that regard. It's more stable if you just use the motor velocity, because essentially you're controlling the same thing. Motor velocity pretty much directly correlates to the rate of change of the output torque, because in a series elastic actuator, the deflection of the series elastic component is the primary driver of the output torque, not the torque at the motor itself. So that's why not only do you have that in the derivative term, that goes directly into the motor driver, which is operating in velocity control mode. And then these blue terms are basically your entire system plant, and then you get your feedback and so on. And so that's how you get from the actual output torque feeding back into your desired torque, and it's changing the motor velocity in order to match it. So if I look at how well this is actually working on that level, I can do step response tests for, I'm just targeting a specific torque load or a specific force load. And I'm targeting also a frequency response test to see how fast it can oscillate between these loads before it starts to fall off and no longer be useful. And so I'm finding that steady state error for both of these, despite no integral term, is basically 0. And the translation axis, I'm able to get a rise time of about 57 milliseconds, which is about right. That's about what I was hoping for. Again, the flexion axis is a bit slower than I was hoping for, and it has this sort of jagged pattern as it goes up, which, to be honest with you, I don't know why. I just don't know why. But that's an anomaly. I assumed that, you know, doing this is averaged over 10 trials. You would think it would smooth that out, but it's apparently repeatable enough that it makes me think there's some actual interfering, repeating, like friction load that happens periodically as it moves. Regardless, when you look at the bandwidth of the system, the translation axis goes up to about 15 hertz, which is more than sufficient for what I need it for. Again, kind of makes sense because I designed this controller to be fast and for alignment rather than specifically like force magnitude, which we still have to take these with a grain of salt because we saw that the force estimation is also prone to some pretty significant error, at least on the way down. The flexion axis, however, is a bit slower. It's at 7.2 hertz, which is still faster than the estimated bandwidth of the actual biological ankle, which is about 6 hertz. But it is kind of on the low end as far as prostheses of this type. Like the biome, I think it's 9.6. So it's got some room for improvement there that I have some design ideas of how to do that. But as for these tests, what I've found is that I can walk on it. It does walk. There's me. I'm wearing these boots so that I can walk on it. They essentially act as stilts so that on the side that I'm not using the prosthesis, my foot is at least the correct height off the ground. And this is me walking. The video sliding forward and back.
I can hear you over there.
Okay, let me mute it, actually. You don't really need to hear it. Yeah, so you should notice that it is sliding forward and back, and as I come off the ground, you do see the toe dipping, and that's it trying to exert that plantar flexion torque, and then it kind of resets as I slide back forward. So overall, it's basically doing what I'm asking it to do. And if I just use this to look at evaluating the load tracking under actual walking conditions, what I find is, as you might expect, again, the flexion tracking is more reliable, probably because the flexion sensor is more accurate. What you also notice is that the difference between the position set point and the actual prosthesis position is pretty large, but that's sort of what we want to see because the difference between these two determines what that load is supposed to be. And if it's matching the load properly, then it's doing what it's supposed to. It's very likely that me walking on it with those boots, I'll go to the next slide just so you can see the two faster. I'm loading it much more heavily than it was being loaded under the simulation, which sort of explains why, you know, I reached over, I think, 120 Newton meters of torque. And you kind of start to notice as my walking speed increases that it starts to have trouble falling fast enough. Like this basically goes from 120 to 0, and it just can't unload that quickly. So that's sort of the only real major source of error, at least in the planar flexion torque tracking, is that it's just kind of a bit slow in unloading, but it tracks just fine as it's being loaded. And just to put those numbers into perspective, like put them all next to each other, I'm highlighting in blue the best result and in red the worst result in terms of accuracy. And as you might expect, at least for flexion, the best result was the slowest speed. The worst result was for the fastest speed for basically all the reasons I mentioned. Worst result for translation was more actually in the 1.1 meter per second walking trial. There's a lot of possible reasons for this, but I think it's important to remember that each walking speed is operating under a different walking controller. So it's kind of not exactly comparing one to one. It's being asked to do different behaviors. So the tracking performance based on that might differ. But this is what we got. And this is effectively showing that you can walk on it at these speeds and it will track load up to this margin of error. So that pretty much summarizes all three of these blocks. That brings me to this block, sort of the last thing before we get to the feedback loop. I'm putting a question mark here because you might be wondering, why didn't we do this? But I'm guessing you're probably not wondering that. I'm guessing you probably know why. I actually had a subject lined up to walk on this before COVID happened, and you know that obviously fell out the window. But you might also be wondering, well, okay, I walked on it, so why didn't we just do a study like that with me as the test subject? And there's a few reasons for that, but basically, I don't think you can really draw any real conclusions as to how this improves user outcomes for someone who does walk with a prosthesis for real. The system is pretty different. I do have some motion in the ankle, which they wouldn't. And it's kind of like being a double amputee rather than a single amputee, where I just have different feet on. And then there's one pretty obvious factor as well that I will try to illustrate here, is that if you know me, I am 6'4". I'm pretty tall. These adapters are about a foot tall, which makes me much taller. You can see that we had to construct some handrails so that I could even reach them while I was wearing these, in addition to the rails that were already on the treadmill. But that's not really the extent of it either, because that's just my effective leg length. What the prosthesis is actually responding to is someone more like this. This guy, we're gonna call him Big Mark, is 7'7". That makes him one of the tallest people in the world. This is Yao Ming and Shaquille O'Neal. I'm 6 inches taller than Shaquille O'Neal in this alternate form. I think if I were a prosthetic subject for a study like this, I would probably be thrown out anyway, because I'm not a very representative sample here, and certainly not represented by the simulations that I was running. So I'm gonna go back to my objectives and admitting sort of the scope where I had to call the project. Did I still meet these objectives? So the first one, did I create a design method which takes optimal simulated generic prosthesis behaviors, translate them into an actual powered prosthesis design? Yeah, I did do that. It's perhaps the powered prosthesis could be refined, but I'm gonna check that one off. I did do that. And then as far as creating a tool set to enable the refinement of a design method based on experimental testing to validate simulated trends. I'm hoping that through demonstrating this process that I have created that tool set. I haven't been able to do the experimental testing to validate the simulated trends, however, which kind of brings me back to our initial question: how do we improve user outcomes? Simulated generic prosthesis, does it work? We still don't know. Still don't know, but now we have the tools to find out. So that is what I'm saying is my main contribution here. You might call this my overall limitations slide, just the fact that this is still a question mark. But that really brings me into the future work discussion in terms of, if we have the tools to find out, what should we do in order to do that? I've been talking about this over and over again, but I'll say it again here. We need to find out if this actually does reduce user energy consumption and socket loading in the real world. Because while it may do that, it's important to find out by how much and why, and analyze the assumptions I made in simulating it to begin with, to figure out how to make them more accurate for some future iteration of this whole process. Related to that are human in the loop studies. I think when you do a lot of simulation work like this and you start looking at the whole human body system and walking as sort of a math problem that can be solved in terms of like predicting how someone will walk based on optimizing inputs, it allows you to kind of have a warped perception or develop kind of a closed off image of how this really works. Like, a lot of people, they're gonna walk on something however they want to, and there's nothing you can really do to change that other than maybe train them. But if they don't like it, they're not gonna use it. And it probably, if they don't like it, there's a good reason for that. And it's worth analyzing how that should impact what your study is saying and what you were trying to do in your simulations to begin with. So that kind of brings in some options to do. For example, if you can put something in their hands that tunes the response of the device according to different simulated weights on the outcome measures, and find out where their preferred ratio is, then that might be a more reliable indicator than my sort of preliminary parametric study of just changing that input and then seeing which one appeared in the middle. Furthermore, we can also look, I limited this to 2 different user outcomes. I focused on user effort and socket discomfort. But there's a lot more that we can look at, including one big one I didn't look at all, which is osteoarthritis risk factors, which might be the next like really major sort of long-term effect that needs to be considered. If we can measure that and come up with a design that reduces that, that could be a whole different project. Related to that also, again, for this, it was just level ground, walking straight ahead. Basically a 2D simulation. There's nothing happening to either side of the sagittal plane. And that's not really how people get around. Even when they're walking straight ahead, like you might have on level ground, you might be ascending stairs, you might need to turn. And it's not just walking either. There's sitting to standing or standing to sitting, etc. There's a lot that can be investigated with just this overall approach, which also might necessitate constructing additional platforms using sort of a similar philosophy. If we move into 3D motion, we probably have to have something that also moves in 3D rather than what I have here, which basically like it turns up and down and it slides forward and back. So like there's a very limited, you know, it's 2 degrees of freedom in one plane, but there might be more to it that we're not looking at. Yeah, so that is actually it. I guess I'll put in my acknowledgements here. That's the extent of my work. I hope you enjoyed it. I have to thank Professor Frank Supp for being a really good advisor for me for the past 6 years. basically taught me everything I know about a lot of this, minus maybe the computational biomechanics, to which I have Professor Brian Umberger to thank. So I appreciate him being here as well. And Professor Ian Gross being one of the first people I ever worked with when I came here, has been definitely a useful and helpful figure for me in the past, and as well now that he's on my committee. I have to thank my lab mates in the MRRL, Sean Wright, Julio, Dr. Eric Burr very recently, Samitra Puneeth, who's graduated forever in our hearts. Same with Yusuf, same with Veen, and Andy, who basically inspired the prosthesis to begin with, given his design, which maybe I'll just show. This is what Andy made, and this is what I made. I don't know if you can sense any similarities. Mine's bigger, but similar principles taken to kind of a different direction. So without his project, this probably wouldn't exist. I have to thank the kinesiology department, especially my colleagues who have helped me a lot. Both of them graduated now, but I have to especially thank Ryan Wedge and Russell Johnson, who have done a lot for me in terms of learning how to actually do these experiments in biomechanics specifically. I have a lot of undergrads to thank for contributing to the project in one way or another. MIE staff, special shout out to Rick and Colby for being very patient and helpful for me in the last month or so as I was frantically machining stuff. AdFab group, Dave Follett printed like half of this for me, including the foot. And yeah, I'm probably missing a lot of people, but all of my friends and family and loved ones for supporting me for quite a long time. And yeah, thanks everybody for being here. I guess I'll take some questions now, if you don't mind.
All right. Thank you very much, Mark. I'll give you a nice virtual round of applause. Very well done. So what we'll do here is we'll open it up to any questions from the general audience. Feel free to answer them, and then we'll have the committee stick around for some additional Q&A. So please, the audience, anyway, you can unmute yourself